Okay, all right. Well, happy Wednesday. It is Wednesday of week 2. And we'll continue talking about Monte Carlo integration and just kind of further develop this idea. I really just look at a couple few examples of it. Okay, so the idea behind Monte Carlo integration is that you can estimate any integral that you want. Okay. Even if you can't actually calculate the integral itself. So as long as you are able to calculate values of the function, okay, you can estimate the quantity of the integral. You might not be able to actually perform the integral, all right? So in calculus, taking integrals can be quite challenging, and so Monte Carlo integration is a way for us to kind of just estimated an integral. The amazing thing, and I don't have any examples of it, is that it can also be generalized to higher dimensional integrals. So you might have double or triple integrals or higher dimensional integrals, and Monte Carlo integration also generalizes to that, although I did not include any examples of that. So, one of the basic kind of things you learn in calculus is that you can get the average value on some interval, and we would say that you just basically calculate the value of the integral itself. So you take the area under the curve from a to b, and then you just kind of divide by the width of a to b, okay, of that interval, right? And that will give you kind of the average value, and so we can say the average value is this. And therefore, if you are able to get an average value, you can kind of say that the value of the integral itself is going to be the width of that difference, b minus a, times the average integral. Okay, and this is all based on kind of the idea that from the Monte Carlo method, we can say that this quantity, if you have a function times a PDF, okay, the function times a PDF, the integral of that is equal to the expected value, okay, of the function h applied to the random variable x, where x is defined by the PDF f. Okay, so this is kind of the quantity, and this is found by basically calculating this function h across random values of x drawn from the PDF f, okay, and then you take the average of them. So this quantity, this is our Monte Carlo estimator for the expected value of h of x, where x is a random variable drawn from f, okay, and that's equal to this integral. And we can and we're able to do this because if you just take the constant 1 over b minus a, that is equal to the PDF of a uniform random variable from a to b. So if you're drawing a uniform distribution on the interval a to b, the PDF of that uniform distribution is 1 over b minus a, and so therefore this whole relationship holds. Okay, right? The average value of h on the interval is 1 over b minus a times this integral, and just kind of working backwards, we can kind of bring that in, and then this is in the form of a function times the PDF, and if we have an integral of a function times a PDF, then we can estimate that using the Monte Carlo method. And so with this in mind, we can estimate the entire integral by just calculating this Monte Carlo estimator, okay, and then multiplying it by the width of b minus a. So we estimate the quantity by just kind of first generating a whole bunch of values from this uniform distribution. We're going to compute h. We're going to apply that function h to all of the randomly generated values. and then we will just take the mean of all of those things. So after you apply h to all of those things, you calculate the mean of them, and then you will multiply it by the width of b minus a. So let's just try a simple function here. So let's say our function is x squared, and we want to take the integral from 2 to 5. Okay, so so you have just you have x squared, and we're going from 2 to 5. And we want to calculate this area here. Okay. So so that's no problem. You could do this. This one's very simple because you could just do it with calculus. So you know the integral of x squared is going to be x cubed over 3, and you evaluate it at 5 and 2. Okay, so at 5 it's 125 over 3, and at 2 it's 8 over 3. All right, and so you take the difference between the two, 117 over 3. The value of this integral is equal to 39. All right, so that's the answer if we were to do it by kind of just analytically. Okay, if we want to do this via the Monte Carlo method, okay, we create a function h, right? So h is just x squared, right? And then we're just going to generate a whole bunch of points from 2 to 5, right? So by doing x as our unit, you know, to 5, from 2 to 5. So we're going to just get a whole bunch of values, right? Maybe, you know, 2.1 and 3.8. And basically every single time I'm just getting, just along here, we're just kind of getting random values. You know, we plug in 2 through 5 here, and we're just getting a whole bunch of values along this entire kind of, I don't know, the function there, okay? So we're just evaluating a whole bunch of these things. So I get a whole bunch of x values between 2 and 5. We're going to plug it into the function h of x, so we're just going to square them all, okay? And so you just get a whole bunch of these things, and then when you compute the mean, right, you're basically just getting, hey, what is the mean of all of these values here, okay? Where there's going to be, you know, all of these things are uniformly calculated, and so you get the average value from here, from 2 to 5, you get the average value to be something around 13, okay? You know, analytically, the true value is going to, the average value is 13, but here, just with 100,000 points, it's 12.996. The width of our interval is 3, from 5 to 2, that width is 3, and so therefore when we multiply 3 by that average value, we get 38.988. So something close to the analytic solution of 39. Again, it's just an estimate, but it's it serves as a way for us to kind of evaluate any kind of function here. Okay. We saw this this example on Monday as well. Here, the length of the interval is 1. Okay. And you have, you know, just a more complicated function, but again, this function can be anything, right? So it could be this, it could be something, as long as there is a function, okay, that can be evaluated. You can plug it in, all right? And again, the analytic solution is going to be 0.9652. 0.9652 if you actually solve the integral yourself. And here we're just going to kind of randomly sample values from 0 to 1, and we're going to just kind of plug in And sometimes we get, high values and low values, and it doesn't matter. So we're just randomly sampling all along here, okay? All between 0 and 1. And so we evaluate them, and then we just calculate, hey, what is the average across all of these things? And when you get that, we get 0.966863. So similar, not exactly the same. And these are just kind of estimates. And so that's kind of, that's the whole thing with Monte Carlo integration is, or all of Monte Carlo methods is we're saying we're happy with an estimate that's good enough. An estimate that's good enough. Okay. Let me give you your first view quiz answer. That's going to be the letter D. D as in dog. Okay. As we do this, okay, the more values that get included in our Monte Carlo estimate, our standard error, okay, our estimate we can expect to become more and more accurate, okay, and that's reflected by kind of this interval here. We can see in the center, the line in the middle, this black line represents our estimate. This is the mean. And then the blue lines are kind of our upper and lower bounds based on based on the standard error of what we calculated. Okay, and so what is the variance of our estimator? This it's a C slide 27, but this is actually from the previous lecture. So in Monday's lecture, we talked about there's a slide that says what is the variance of this Monte Carlo estimator, and basically the more values you include as far as estimating your thing, the more accurate you can expect it to be. Which I think makes intuitive sense, right? If you're basing your estimate based on a small sample of say 10 observations, you can't expect it to be very, very accurate because my 10 observations and your 10 observations, there might be a significant difference between them, so we expect a higher standard error between them. Whereas if I had 1,000 observations and you have 1,000 observations, I would expect the mean of my 1,000 observations and the mean of your 1,000 observations to be very, very similar to each other. Okay, and as we have more and more of these things, like 1,000,000 observations, the mean of my 1,000,000 and the mean of your 1,000,000 also going to be even closer to each other, just because as you're getting a larger and larger sample, basically the variance of that estimator, of that sample mean, is going to get smaller and smaller. Basically by square root of the sample size, and so that's reflected here. The math for it is in Monday's lecture, and so we see it shrinking as it goes on. Okay. Right. So this feels. I want to kind of just demonstrate this next thing, right? So another problem that we might have, okay, and again, this is kind of silly because we have a function that does this, but in statistics, the standard normal PDF, it's kind of known that you can't take the integral, right? There's no closed form solution to the standard normal, or just the normal PDF, right? If you take the normal PDF, we don't have a closed form solution for the integral. We do have a function that works for giving us the cumulative distribution function, the CDF of the normal distribution, and that's P norm. So this problem is already solved, but the question is can I use Monte Carlo integration to kind of still solve this problem? Okay. We have this normal distribution, and then wherever you pick some value z here, and we want to get, what is this? What is this in it, right? So this is going from negative infinity to z of basically f of t, or whatever it is. I guess this is x, but letter I used was x there. But we want to know, okay, what is this solution going to be? So this seems, a little bit strange, because if we're approaching this as a kind of a Monte Carlo thing, how can you evaluate the integral, especially because this goes down to negative infinity, right? It goes down to negative infinity, and so how can we can't just kind of take this normal approach of trying to generate random values from minus infinity to positive infinity, because that's just not going to work, right? So we have to be a little bit creative, okay? All right. So what we're going to do is we're going to just kind of create a simple indicator function, right? And we're just going to have either a 0 or a 1, okay? And so basically, if some value z is less than x, we'll put in a 1, and if it's not, we're going to put in a 0, okay? And so if this indicator, the expected value of this indicator function is just going to be equal to the CDF, okay? Because we're just going to say the probability that basically if z is less than or equal to x, this is effectively what we're going for, okay? We're going to say z comes from the standard normal distribution, so we're going to say the probability that z is less than or equal to x is going to be the probability that z is less than or equal to x, and then we're going to put in a 0 for this. So this is the expected value for the different things. Okay, the probability that z is going to be greater than x. Sorry, this should be x right here, not a 0. Is going to be we multiply that by 0. So the expected value of this is just going to be f of x, and so what this requires is us to be able to generate values z. Okay. So now that we have the integral of interest as expressed as an expectation, we can use the Monte Carlo estimator to estimate this. So the key here is we're not going to generate values from the uniform. Okay. Instead, we're going to generate values from the standard normal distribution. Okay. So now it becomes almost like a trivial problem. Okay. So because if we were trying to generate values from the uniform, I would have to generate it on the interval from negative infinity to positive infinity. Okay, but now we're going to assume, okay, we can assume we're going to be able to generate z from basically the normal distribution. Okay, so we're going to generate a bunch of normal values, and then and now it's almost trivial, because so z could be, technically it could go anywhere from negative infinity to positive infinity, okay, with just kind of a high probability that z is between, say, 3 and negative 3, or 95% between 2 and negative 2. And then all we're going to do is we're just going to calculate, we're going to just ask, is z greater than or less than or equal to x? So, you pick an arbitrary value. If you generate, a value down here, this will be a 1. If you generate a value over here, you're going to put in a 0. If you generate a value, you get a 1. And so basically, you're just generating values along the number line, okay? Some of these things are going to be below x, some are going to be greater than x. we're going to put in, we're going to calculate ones that are less than x and zeros for things that are greater than x, okay? Effectively, we're just going to generate a whole bunch of random normal values, and we're just asking what proportion of those values are less than or less than x, okay? And so this seems, it feels almost trivial if we're given the fact that we're able to generate random normal values, okay? If we're able to generate values from the normal distribution, we're just going to generate a whole bunch of values, and we're going to ask what proportion of those values are less than, some quantity x. So it's just basically the indicator function here is, how many values of z are less than or equal to x. You divide by n is now you're basically asking what proportion of the values that you generated are indeed less than x. Okay, and so this thing can be generalized to produce the estimator of the CDF of any random variable as long as you can generate values from that random distribution. Okay, so it's silly and it is expensive. It's very computationally expensive, but at the same time, it works, right? So let me, what is going on here? All right, let's update. Okay, so I'm going to say z is going to be basically our norm, and all right, let me just do 100, let's do 100 values. Okay, mean 0, standard deviation 1. Okay, so these are my 100 values of z, and then let's say I want to estimate, p norm of, I don't know, 0. Okay, so the true p norm, true value is 0.5, right? 0.5. Basically, what is the cumulative distribution function of standard normal values that are less than 0? That's going to be 0.5. And here, I'm basically just taking my values of z, and I'm going to ask how many of them are less than 0, okay? And then we're going to ask basically what is, we're going to convert these to integers, okay? That's basically so the indicator function is you just take your trues and falses, turn them into numbers into ones and zeros, and then you calculate the mean, right? So technically you don't even have to, R is automatically going to make them numeric, okay? So this is not a good estimator, right? Out of 100 values, 58 of them were less than 0. So right now my empirical estimate is 58%. Okay. If I run this whole process again, okay, and I do another 100 random values, and I calculate, the proportion. Here I got 51%. Another random set of values, I get 45%. Another set of values, 52%. So in the long run, we expect it to get close to 50%. But yeah, anytime I just do this, say with 100 values, it's not necessarily going to do great estimates. So let's do 100,000 values, and the mean here I get 0.50135. Whoops, another 100,000 values. So as I get larger samples, we expect the mean to get closer and closer to the actual value, right? And this doesn't necessarily just have to be, so I still have my 100,000 random normal values, and I can just say, hey, how many are less than, say, 1.96, okay? So p norm of 1.96 we expect to be around 0.975, and so in our thing with 100,000 values we get 0.97483. So kind of close, but also leave something to be desired. Okay, and again I'll just generate another set of values, and we're getting something again close, but not quite, right? So we can estimate basically the normal CDF, okay, of any value, whether it's 1.96 or something, by kind of generating a whole bunch of random values from the normal distribution. We turn those into zeros and ones, and if it's less than 1.96, it's going to be a 1, and if it's not, it's going to be a 0. And basically we're saying that out of 100,000 random values that we generated, 97,530 of them were under 1.96, and so therefore my empirical estimate is 0.975. Yeah, question.
Is there like a practical upper limit to like the amount of samples that you want to?
Yeah, so I've got a slide kind of talking about this. Is there a practical upper limit? I mean, so you're limited just by kind of how annoying it is, like how computationally expensive it is to generate these values. And so right now, generating random normal values for a computer is pretty, it's not super computationally expensive. I mean, it is like, this is a terrible way to go about it, okay? But it's also not, I guess there's a, okay, so let me rephrase all of this. So, I could generate, I don't know how many values I want to do, like 10 to the 8. Let's see how long that would take. It takes a while because that's a lot of values. Okay, maybe I've broken my computer. Okay, it did it, and I can ask, okay, calculate what is the mean of all this, and again, it takes a few seconds, and we get something around 4 decimal places of accuracy. Okay, at the 5th decimal place we're off. Okay, I mean, I don't, and that just might be the sample. So this takes a while. And so is there an upper limit? There's no upper limit. It's just the more you like if I went to 10 to the 9, it would take however many seconds it took to do 10 to the 8. 10 to the 9 would take 10 times longer generally. Okay. And then that would probably just squeeze out maybe one more decimal place of accuracy. So, there would be practical limitations of how you want to go about this. Okay. In general, the rule of thumb is if you don't have to use a Monte Carlo method, don't use a Monte Carlo method. Okay? If you have an analytic solution, use the analytic solution. If you have any way to go other than a Monte Carlo method, don't use it. Okay? But the Monte Carlo method is here and it's used and it's popular because a lot of times we don't have any other choice. A lot of times the math to do the actual thing is too complicated, so we just run a whole bunch of simulations. That's how all kinds of predictions are being done. So if you go to websites where they try to predict the outcome of the election or to predict the outcome of some sporting event, we don't have just some magical answer, but they have ways to simulate results. And so they just simulate the results, and then they simulate 10,000 results or 100,000 results, and then they take the average of these things. So they have, depending on how accurate their simulation model is, they just say, all right, let's have these two teams play against each other. And I don't know if you ever bought a sports game on your console, but you can artificially set up a match between two teams on your thing, and you just have it play the game plays out, right? And because of just different random things, sometimes team A wins, sometimes team B wins. And if you have a very good, accurate model that simulates it, and you just run it a whole bunch of times, you might be able to get some kind of result there. Okay. So this is kind of stupid, but it also works. All right, in that we're able to generate a bunch of values from the normal distribution, and then we can say, okay, out of this. What is 10 to the 8? That's 100 million or something. Okay, out of 100 million values, what proportion was less than 1.96? And the answer was 0.975, right? I can say, okay, out of 100 million, what proportion was less than 0? And we're hoping it's going to be close to 0.5, and indeed it is close to 0.5, but it's not exactly 0.5, right? How many are less than negative 1.96? So this is just an empirical estimate, and we're getting something close to 0.25. You know, what proportion is less than, I don't know, what's another 1.28 should give us around 10%, okay? And indeed, you know, we've generated around 100 million of these things, and we're getting kind of close results, okay? So anyway, this is all to say the normal CDF is effectively, you know, a Bernoulli random variable where our probability is equal to the CDF here, okay? So here I just said how accurate are the estimates that we're getting. Oh, you know what? Let me give you your second view quiz answer. It's the letter C. C as in cat. C as in cat. So here I generated 100 million values, 10 to the 8. And if I wanted to, I could have generated, you know, even more, but it would have taken a computer even longer to do that. And you know, the question is if I have 100 million versus 10 million versus 1 million, and I wanted to kind of estimate these quantities, all right, how accurate does it have to be, right? So Q norm, say 0.999, is 3.09. So if I plug in P norm of 3.09, okay, we would expect, this is the true answer, something around 0.999, 0.99899, okay? And I can ask how many values out of 100 million is less than 3.09. Or I could be more accurate, 3.09232. So out of 100 million, what is that? 999,000? No, 90. I can't even read this. Something. 99 million. Okay, a lot. Yeah, I think 99 million 900,040. Okay, so almost if versus P norm 390232. Okay, so we should have gotten that. Okay, and so here I just kind of calculated. So the true proportions should be these numbers, and across this slide. Okay, so these would be kind of the cutoffs. So at 0, if I just took 100 random values, just kind of on one run, I got 52 out of 100. Okay, out of 1,000, 490. Okay, out of 1,000, so my proportion is 0.49. Out of 10,000, we got 4,992. Out of 100,000, I got 0.50082. And so as the number of kind of trials increases up to 10 to the 8, okay, I'm getting, you know, kind of one more with, as I increase this, we're squeezing out, you know, kind of like one or half another decimal place of accuracy. Similar kinds of things. So the 75th percentile is, you know, right around here. The cutoff is, you know, 0.6745. So we expect around 75% of, you know, random normal values from the standard normal to be less than 0.6745. And we see that, you know, this gets closer and closer as we get more of these things. But, you know, every step down here requires 10 times as many random values, okay? And so you kind of have to judge for yourself, you know, how much more worth it, right? To go from 10 to the 7 to 10 to the 8, okay, this requires 10 times as many random numbers. It's 10 times more computationally expensive, and how much more accurate of a number are you getting, okay? And comparing these two things are very similar to each other. In fact, these two numbers, they're like, on the same order here. And again, all of these things are subject to randomness, so you kind of just have to ask, exactly how much error are we reducing, and everything kind of by like the square root of n is your factor. So when you get 10 times more values, you're around 3 times more accurate, okay? Or I guess your standard error shrinks by around a factor of 3, okay? And so if you wanted to squeeze out one entire decimal place, like if you wanted to shrink your standard error by a factor of 10, you would need 100 times more data, okay? And that's kind of the limit. And so, as far as where is kind of your practical expense, you just have to say, well, okay, if I want one more full decimal place of precision, then I would need 100 times more random values generated, okay? But you can see, especially for some of these more extreme values, we are getting reasonable estimates, okay? So if the true value is 0.9999, we are getting, kind of close to that, okay? And this is based off of, 100 million versus, out of 1,000, 998 were less than this, okay? Out of 10,000, 9,994, so we got 6 out of 10,000 greater than that. And so, our numbers are kind of close, but again, everything is subject to randomness, okay? Just kind of by coincidence, we happen to get it exactly right all of these times. But that's what we're seeing here, okay? So, and again, this is not limited to the normal CDF. So basically, any kind of CDF that you want. So if you have the t distribution, okay, so you could generate random values from the t, okay. We'll call this x. I can say, give me 1,000,000 random values from the t distribution. Degrees of freedom, 10 degrees of freedom, okay? And we can kind of compare that to say, all right, what if I plug in 2.2 with, not p norm, t degrees, with, okay? So if I plug in 2.2, I would expect 0.9737795. That's the true answer, and I can just kind of get my indicator function. So I would just do it as numeric. How many values of x are less than 2.2, and then we would calculate the mean on that. And so this is my estimated value versus the true value. Okay. Again, this is a stupid way to do it because we already have this function p of t. All right, that gives me the CDF. But this is all dependent on just my ability to generate random values. Okay, so if we are able to generate random values from some distribution, whatever it might be, okay, whatever it might be, if we can generate values from that particular distribution, we can estimate the CDF just by generating a whole bunch of these things. We're effectively just kind of manually calculating the empirical CDF there. Okay, so how many values do we need? If you want, so a conservative estimate of the variance is going to be 1 over 4n. Conservative error estimate of the standard error is going to be 1 over 2 square root of n. Okay, because that's where the maximum variance occurs, where the proportion is 0.5. So as you get closer to the edges, which is what we have over here, this quantity, basically p times 1 minus p, which is kind of your variance of a Bernoulli thing, okay, over n or whatever, it looks like this, right? At 0 mole, and it's maximized at 0.5. So as far as your standard error goes, your kind of conservative estimate is 1 over 2 root n, and so therefore if you want to squeeze out an extra decimal place, you need 100 times more data. And so if you want your estimate to be accurate to around 4 decimal places, you probably need around 100 million values, which is computationally expensive. And if you want 5 decimal places, then you would need 10 billion values, which I think most people would agree is overkill and impractical for us to execute. Okay. But anyway, this whole thing regarding Monte Carlo integration can be used for any kind of thing, and just with a little bit of creativity, can be generalized to things even unbounded spaces if you are able to generate values on that kind of random interval. We're going to expand on this into something called importance sampling, which in my opinion is a bit of it's not a very good name for it, okay? But on Friday we'll take a look at importance sampling, where we're basically taking Monte Carlo integration and rather than just, and we saw a little bit of it today, rather than generating values from the uniform distribution, we'll start generating values from different distributions that are kind of more aligned or better aligned with the integral that we're trying to estimate. So we saw a little bit of it today with the normal CDF, where we're generating values from the normal distribution or whatever kind of random probability distribution that we want. And then on Friday, we'll expand further into that, looking at a whole bunch of other distributions. Okay, we'll wrap things up here. And let me give you your final view quiz answer.